3.3 Rules of Differentiation. We want to go ahead and start with the constant rule. We're saying if you were given a function f of x such that it equaled 2, I can go ahead and graph it. This is the horizontal line when it crosses the y-axis at 2. We know for horizontal lines we have a slope of 0. Remember, our derivative is approaching some point that we want to know what the slope of the tangent line is. In this case, the tangent line is the line itself, and its slope is 0. So for any constant number, so if I was given a function y equals 6, taking its derivative should be 0. We want to go ahead then and use the power rule. Remember, this is one of our most important ones that we do almost most of the time when we have some kind of exponent, even including when it's just an x to the first degree. So using this rule, we can have, for example, x cubed. It's saying to find its derivative, you bring the exponent down as a factor in front, and then you subtract 1 from the exponent. So we now have 3 times x squared for our derivative. We have constant multiple rule. Think about this. If I was given f of x is equal to 4x cubed, I could, in a sense, break this 4 out separately and do my power rule with what's inside the parentheses, the x cubed. So if I want to take the derivative, I'm going to set it outside and take the derivative of the inside. So I have the exponent coming down, subtracting 1 from the exponent, and now it's just all multiplication, and I can multiply in front and get that situation there. So this is that constant multiple rule that we can still apply to our power rule. The sum rule is saying if I have two functions that are being added, I can add their derivatives. So let's take, for example, if f of x is equal to x squared and g of x is equal to x, I can find each of their derivatives separately. F prime would be 2x, and g prime would be 1. So this sum rule is saying if I wanted to do the derivative of both functions, I'm just adding each of those together. But if I want, instead of writing all this out as much as I have, if I wanted to say this function was really x squared plus x, and then I want to try to take the derivative of that all at once, I'm still going to derive each function separately, and I get the same answer. All right, the number e. Remember, number e is such a special, unique thing we find using a lot of applications. We have on page 157 in our workbook, our textbook, and I had offered this as a bonus question. What special exponential function, when we're approaching 0, what is the slope and everything? And then from here, we can see that if we had, for example, the exponential function 2 to the x, as we're approaching the point 0, 1, its slope ended up being about approximately 0.693. And y equals 3 to the x, approaching the same point, its slope approached to be about 1.099.